Hello, welcome to part 1 of 2 of this lecture on sedimentary rocks. This is the first of our lectures where we're going to dive into hard rocks and start looking to the past. So I'd like to start out this lecture by thinking about what actually defines a rock and a brief overview of different rock types. We'll then get into the actual types of sedimentary rocks, the textures that we find within these rocks, and what that tells us about paleo environments. We'll chat a little bit about Steno's principles and get into some paleo environmental reconstructions. Before we get too far along, though, I'd like us to consider this question of how would the world around us look as a rock? And I don't mean if we were a rock, but if the world suddenly turned into rock, for whatever reason, it got buried, it got lithified, and we're looking back at it a million years later, what would we expect to see? So what I would like you to do for today and for your homework is to choose a location in the world, somewhere you can picture fairly easily. And it doesn't matter if this location is urban or rural or some mix in between, either one will work. And we want to ask ourselves this question: if this location became preserved in the rock record, what do you expect to see in that preserved rock? What textures would there be? So think about this now, come up with a hypothesis, and we will explore this question over the course of these 2 lecture series. I have to put on my headphones because my computer is starting to make a lot of noise. Okay, hopefully that'll be a little bit quieter. All right, so let's dive into rocks. What is a rock? We're going to define a rock here as being consolidated, which means it's not made of loose material. In each of these examples of the rock, everything that makes it up is solidly joined together. It does not fall apart when you pick it up. Rocks are naturally occurring, and they're composed of minerals. So we'll talk more about minerals in your lab this week, but basically they are going to be the chemical building blocks of our rocks. And many of our rocks are composed of more than one mineral. However, we'll have a few exceptions where only one mineral exists. There's 3 main rock types, one being igneous rocks, which we'll talk about tomorrow. These cool from magma or from lava. They can form either underground from magma chambers that have cooled, in which case we call these plutonic rocks, or they can form at the surface of the earth as magma erupts into lava and that lava cools. And these form volcanic rocks because they form from volcanoes. These igneous rocks are made up of minerals that interlock together and to kind of create a crystal mesh. So these are all, pictured here in all these different colors are different minerals that are meshed and interlocked together to form the igneous rock. In contrast to that, sedimentary rocks are actually formed of bits of other rocks or fossils. So rather than the minerals being the building blocks, the bits of other rocks and fossils are the building blocks here. They form through deep pressures and temperatures. So as these bits of other rocks and fossils are deposited along the ground, they then get buried and consolidated into a sedimentary rock instead of just a pile of other rocks. And they have a range of textures within them, which is going to represent where on Earth they were formed, or if you were going to a different planetary body, where on that planet and what type of environment on that planet were these rocks formed in, right? So these are 2 examples here where this lower one contains a lot of fossils, and that tells us where this rock was originally formed based on where we can find those fossils today. All right, the last but not least of the rock types that will go over on Wednesday are metamorphic rocks. These are formed from pre-existing rock, could be sedimentary, could be igneous, but they undergo high pressures and temperatures. So they're buried or they undergo a lot of forces, and that creates not exactly melt of the old rock, but it reforms the minerals and the structures that were in the rock. So the key here is that these high pressures and temperatures are not melting the rock. We're not getting molten rock again, but we're getting high pressures and temperatures that can reform parts of these rocks. And so this brings us to the rock cycle. How are these three related? So we'll start out with kind of going towards sedimentary rocks. Sedimentary rocks are made of bits of other rocks. And so those other rocks could be bits of metamorphic rocks. They could be bits of igneous rocks. They could even be bits of sedimentary rocks, which are eroding and depositing and making itself again. A key factor in this relationship is this last step of lithification. So more than just the erosion of metamorphic and igneous rocks into smaller rock particles, we need those smaller rock particles to then undergo pressures and temperatures that lithify them so that they are consolidated. Now, if we look at igneous rocks are going to form from a magma or a lava. But that magma or lava could originate as a metamorphic or sedimentary rock. These metamorphic and sedimentary rocks, or even an igneous rock, undergo high pressures and temperatures high enough to cause melting of them, so they get included back into a magmatic form. And then that magma cools through a process called crystallization. This is essentially the cooling process by which mineral crystals are grown. Right, and lastly, we have the arrows going towards metamorphic rocks. So again, these could be sourced from igneous or sedimentary rocks or even a metamorphic rock. But in either case, these rocks have to undergo some high pressure and temperature that doesn't melt the rocks but causes some reorganization. This process is called metamorphism because you're metamorphosing, changing the form of the original parent material. So today we're going to focus on this corner of the rock cycle and sedimentary rocks. And throughout the week, we will touch on each of these rock types and then kind of bring them together to look at geologic time at the end of the week. All right, so moving on to sedimentary rocks, we have two main types of sedimentary rocks that we'll cover today. The first are clastic rocks, and these are sort of the traditionally thought of sedimentary rocks. They're made of other rocks that have broken up through weathering and erosion, and then they've been lithified into a sedimentary rock. So we'll go over that creation. We'll go over how we name different rocks. So they're not all sedimentary rocks, but have their own unique names depending on the size of those other particles and depending on the textures. After we go through clastics, we'll touch on chemical sedimentary rocks. So rather than being made of rock bits of other rocks, you can think of these as the byproducts of chemical weathering of other rocks. So they're going to be mostly made of the ionic components. They're created through processes like precipitation and evaporation of waters and brines. So we'll talk about some subsets of that: evaporites, carbonates, and biologics, chemical sedimentary rocks. Okay, so first let's start with our clastic sedimentary rocks. These are formed as exposed rock on Earth is weathered, usually through mechanical or physical weathering processes. If you remember from week one, this means that the rock is being broken down into smaller bits, but it's not changing its chemical formula. These weathered rocks are then eroded, and they can be transported through a variety of means, wind, water, and ice being some of the most common ones. In that process of erosion, just to give you a sense of the scale of what's going on every year, we have glaciers every year are going to erode and transport about 10 to the 4th to 10 to the 5th tons per year of rock. Wind, through the transport of dust and the transport of sand in dune-like environments, is going to end up transporting 10 to the 8th tons per year. So even though wind may seem, at least to me intuitively, wind seems like a less powerful force than glaciers are, it is more prevalent, and there are a lot of dust particles too. But topping off both of these are rivers, which transport about 10 to the 10th tons per year of material. After these materials are transported, they eventually get deposited and then lithified. So deposition occurs when that energy decreases and the material can no longer be transported. So for example, as rivers come out of the actual rivers and meet oceans, as this example shows on the right here, the flatter slope of the ocean causes the energy to decrease within that system. Without that energy, particles can no longer be transported. There's nothing to do the work. And so these particles are deposited right at the base where the river meets the ocean. And so this is how we get the formation of bodies like deltas. If this occurs on surfaces, so if this was land instead of ocean, we get a feature called an alluvial fan. And essentially both these deltas and alluvial fans are just showing us there's a change in energy, a decrease in energy, material can no longer be transported, and so it gets deposited. These examples were from rivers, but you can see this with glaciers. At the terminus of the glacier, there tends to be a lot of debris because we've lost that transport power. Same thing with wind. As the wind dies down, we'll see all the dust and the fine sands and silts that were carried by wind kind of falls out of the air and is deposited on the ground. So this is the first step in creating clastic sedimentary rock. However, as they're deposited, they're just loose material. They haven't become compacted and consolidated yet. And so this is that second process of lithification that's really needed to create that sedimentary rock. So lithification is basically the process by which we take that deposited material and turn it into a cohesive rock via compaction and cementation. So compaction can occur, for example, in this delta here, as particles are deposited on the floor of the delta. Eventually, more and more particles are deposited on top of them, and so we kind of go down in this chain here. The additional weight of all the particles on top of it starts to compact everything underneath, which squeezes out any remaining water until we get this really tight packing at the bottom. This process, as you can imagine, can take a lot of time. So this could be, depending on the speed of this burial, this could take millions of years or tens of millions of years. Once these particles are compacted, the water that's flowing through those pore spaces will often contain a lot of ions, mostly of silica, maybe some carbonate, and they start to precipitate those ions out into a solid form. And those solid forms act as cement that binds all of the particles together. So this is an example of cementation. So here we're looking through a microscope view of a sandstone, and all of these white particles here are the grains of sand that were deposited. And between those grains in blue are all of the pore spaces that were left behind. And whatever water was flowing through these pore spaces contained a lot of calcium, a lot of carbonate, and so it precipitated out calcite, which is calcium carbonate. And that calcite bound all of the sand grains together to create a cohesive rock. So once a process of lithification has occurred, we now have a clastic sedimentary rock. Through other processes of erosion and uplift, those rocks will eventually be brought back to the surface. And once they're at the surface, we can start to name them and describe them to try and interpret what those past environments were that the rock formed in. So we'll start out with some naming conventions here. And for clastic sedimentary rocks, it's fairly easy. They're named mostly based on their size. So we'll go through this table that shows the size of the rocks, the resulting rock name, and then if we had a lab class and it was not a pandemic, some things you could do to figure out if it was the right rock. So starting out with the smallest grain size are clays. So we mentioned last week that clay is also a type of mineral. It is also a size of grain in sedimentary rocks, and it's usually made of the mineral clay. But these clays are really small particles. They're less than 1/256th of a millimeter, so you really can't feel them. If you could hold it up in your hands, clay would feel very smooth as you rolled it around between your fingertips because your fingertips are unable to distinguish the individual clay particles. When clay is deposited and lithified, it forms a rock that's called a shale, which is sometimes known as a clay stone. The pictures on the right show what some of these look like. They tend to kind of break off fairly easily into sheets, and they tend to be fairly dark in color. They look a lot like dried mud, in fact. If you weren't sure if you had a clay stone in the lab, you could lick it. Just like rolling it around between your fingertips, the clay stone or the shale will feel very smooth in your mouth when you lick it. So it's one way to distinguish the two. When we go up in grain size, we get to silts. So these are marginally larger than clays. They range in size from 1/256th of a millimeter to 1/16th of a millimeter. So this is getting to a grain size that we can start to make out with our naked eye, but we may not be able to see the individual grains. Instead, we will get a impression that there are individual grains, which these two images on the right kind of show. If you contrast that to the last slide, this clay stone is much smoother. And these silt stones, the sedimentary rocks made of silts, do have some textures to them that indicate there are grains that you can start to imagine are there. And if you have a hand lens or some magnifying lens, you may be able to start to see them. And the differentiation between clay and silt in terms of feeling it and putting it in your mouth is that the silt starts to feel gritty. So again, if you take a pile of silt and you rub it between your fingers, you're going to start to feel some grittiness. And when you put a siltstone into your mouth, you can start to feel some grittiness of the rock. It no longer feels smooth like the clay stone. Again, I would not recommend doing that right now, especially if you are sharing rocks. So clays were mostly dark in color. Siltstones can range in color. So we have an example here that's dark gray and one that's tan. All right, if we move up in grain size, now we can start to see these grains. So sand grains are defined as being between 1/16th to 2 millimeters in size. So this is the size we can see with our naked eye. So there's no need to put it in your mouth in this case. And we call sedimentary rocks made of sands sandstone. And these are some images of sandstone. So you can see in relation to the penny scale, the individual grains, they kind of show up as these black and white speckles in this image here. The image on the bottom, we get the sense of individual grains because we see some layering of different colors, right? And that's going to start to pick up more with our sandstones, where we start to see different colors within one rock. Okay, and then finally, the largest size that we'll deal with is anything larger than 2 millimeters, which we'll call a gravel, but these could also be large enough to be pebbles or presumably boulders. And these are called conglomerates. Again, you don't need to put this one in your mouth. You will be able to see it fairly easily. The examples on the right are pretty typical examples of conglomerates. So you've got rounded pebbles of other rocks that are bound together and cemented together to form the conglomerate rock. Unlike sandstones through shales, where they tend to be made of mostly one or two minerals, conglomerates can be made of bits of other rocks, which we call lithics. And you can kind of see that in this image here. All of these individual rocks have a wide variety of colors and textures that represent the original parent rock. Okay, so that's how we name our sedimentary rocks, and they can give us some idea of where and how these rocks were deposited. So each process of deposition is going to leave behind some unique sizes and shapes that are encoded into the sedimentary rocks. So we'll go through a few of these properties. The first one being the grain size, which is directly tied to the last few slides we've been talking about. So the grain size of the rock is going to reflect how much erosion and transport it's undergone. If you imagine a rock starting out and it starts to be transported, the rock is usually not being transported in a free fall with no interaction with anything else. Instead, it is rolling and tumbling and colliding with other particles. And as it does so, it's going to start to be bashed and eroded away into smaller and smaller pieces. So the grain size is a reflection of the amount of transport, where from less transport to more transport, we start to wear away at the grain and we get smaller and smaller sizes as more and more transport occurs. So for instance, something like a siltstone would have occurred under a lot of transport, whereas a conglomerate may have had relatively less transport of the original material. Right, so just to follow up on that, which underwent more transport, a shale or a sandstone? Since the shale has a smaller grain size, it likely underwent more transport because it's been knocked about a bit more into a smaller size. All right, the other thing that we think about is the degree of sorting. So sorting in this case refers to the range of grain sizes that we find in the rock. Even though we group things by one grain size, you can have sandstones that contain some shales or that contain some clays or silts in them, just like you can have conglomerates that contain some sands and some clays and some silts. And this range of grain size is going to be driven by the rate of deposition and how it was deposited. So we call something well sorted if it has mostly the same grain size, and something is poorly sorted if it has multiple grain sizes to it. So a shale, because a shale can only be made up of clays, is going to be very well sorted, whereas a conglomerate is going to have very poor sorting. And in general, this does respond to the rate of deposition. Conglomerates tend to form in environments with really rapid deposition. So these could be things like a landslide or a river flood where something happens very quickly and then it deposits out and lithifies. Versus a shale may form under conditions with much more slow deposition. So we often see shales off of deltas where you just kind of have this constant influx of fine grained material that is settling out onto the seafloor. So again, we kind of just went over this, but which has higher sorting and thus more gradual deposition, siltstones or conglomerates? So a siltstone can really only be made of silt. It maybe has some clay and some sand, but there's really much more confined range of grain sizes that it can have. And so this relatively better sorting means that it has a slower rate of deposition than the conglomerate. All right, and then last we can also think about the shape of the grain. So this is going to matter more for the sandstones and the conglomerates because we can't see the grains in siltstones and clay stones or shales. When we think about grain size, we think about whether it is angular or round, because that's going to reflect the transport time as well as the transport mechanism. So if you imagine we start out with a fairly angular piece, so this is freshly weathered away and is fresh into the transport system. As that is bounced around with other particles, all of these protuberances are going to be the first things to go. And so over time, with more impacts, it's going to take on a more rounded or spherical shape compared to its original shape. So a round shape is going to be a longer transport, and angular is shorter transport. We tend to get shorter transport with things like landslides and different types of landslides like debris flows, versus this longer transport is going to be rivers, wind, for example, with glaciers kind of somewhere in between. So there's a whole spectrum of angular to rounded. We can go from angular to subangular to subrounded to rounded. And some examples of that: angular debris might be kind of what you're used to seeing as you walk out onto paths around here. A lot of the kind of pinkish rock that we've laid down is angular debris coming off of Pikes Peak. If that debris had been transported in a stream for a while or transported by wind, we would start it to get a more round debris with more of a spherical look to it. Okay, and once again, I've covered up the text, but below this it says, what grain shape would a landslide produce? What about a river? So because a landslide is a fairly fast and chaotic movement, we would expect to see more angular grain sizes that are probably poorly sorted, and or grain shapes, not sizes. And then a river would tend to have well sorted grains that are fairly round. Okay, so in addition to the kind of the size, shape, and sorting of the grains, we can also see patterns within the sedimentary rocks that give us clues to how they were deposited. And so the first of these patterns we want to talk about is bedding. Bedding is a planar layered structure that we see in sedimentary rocks. I'm showing you 3 scales of this here. So on the far left is sort of an outcrop or hand sample scale. So you can see all of these layering to the sedimentary rock. Those are the individual beds. We get to a slightly larger outcrop scale with people for scale here. We can see that the bedding can be on the order of 1 meter to decimeters thick. And then we can get even larger bedding, which is called massive. So in this case, there's almost no bedding. We do see some, what looks like some evidence of layers here. However, I think those are just an erosional remnant. So this is common when we have glaciers and landslides because they are a very rapid process. And so they tend to leave behind no bedding in the sedimentary rocks. So there's different types of bedding. We can find bedding that is parallel to itself, which tends to form in still water. So you need to have kind of deposition falling out of suspension, perhaps from a lake or an ocean, and falling onto a flat surface that is not getting interrupted in any manner. So you don't have waves that are eroding that sediment away. We tend to see these in fairly fine-grained environments. And again, that ties back to the energy level. Those finer grains are going to be lower energy, and that lower energy is necessary to have still water deposition. If we get into slightly higher energy environments, we can get a type of bedding called cross bedding. And this occurs when we have dunes or ripples that are migrating. So this could be in desert or beach environments where wind is driving it, or this could be in rivers or tidal environments where you have water creating dunes or ripples. So this is a nice GIF of how this forms. As the dune is migrating, it is depositing on the lee slope and eroding away on the upwind slope. So it's taking material from upwind and moving it downwind. And as it moves it downwind, it's being deposited in these angled layers. And these angled layers are preserved in the sedimentary record. And what is also preserved is the base of the dune itself, so where it's eroding from, which often creates this sharp contact with other dunes or ripples. We can get these forming in both wind and water-driven environments. However, the wind-driven dunes tend to be a bit larger and also finer, more even grain sizes. So here are two examples of what these crossbeds could look like. This one is at an outcrop scale, and if you go to places like Red Rocks, you'll see a lot of these preserved there, especially if you kind of start from the middle parking lot and make your way directly up those paths uphill. You'll see a lot of crossbedding. We can also see it at finer scales. So here is just a rock hammer for scale to show that you can have meter scale crossbeds or you can have decimeter scale crossbeds. And then this GIF is taking a while to load, but this is an example of an outcrop and then how somebody has interpreted where the crossbeds are and then where the bedding is that separates each of the crossbed sets. I'll watch that one more time. All right. Cool. So we've kind of gone through a whole listing of sedimentary clastic rocks, the grain sizes, the textures. But now let's try and bring that back to how we can tell these geologic stories and the stories of the Earth. And this is going to rely on a principle called uniformitarianism. This is essentially this phrase, the present is the key to the past. And it means that the things we observe today, the sort of processes, they were probably acting in the past. So if we see a dune environment today that has ripples, and if we cut away into that dune, we see things like crossbeds. It means if we see similar features in the rock record, like this, that those rocks were probably formed in a similar environment. So we can start to interpret what we call paleo environments. By comparing the textures that we see in rocks to the textures that we see in modern deposits. And this is part of the reason we started out with the modern world in week 1, and now we're moving to the past world. And it's important to note that we think of this as processes that can be compared from modern to the past. We need to note that the rates can differ. This is especially true as we think about how to predict things out with climate change. We know the processes, but now we're considering new rates of processes that are known. Okay, so that ends our clastic rock section. In part 2, we'll look at the chemical sedimentary rocks, and then we'll play around with uniformitarianism to try and draw out some paleo environment reconstructions. As you are ending this first part, I'd like you to think back to this question at the beginning of how would the world around you look as a rock? And now that we know about clastic sedimentary rocks, consider, is your location, is that going to be preserved as a clastic sedimentary rock? And if so, what types of textures and grain sizes do you expect to see? What would you name it if it is a clastic sedimentary rock?